nothing was apparent, but if you're quite astute, you may notice that little region over there, okay? And if we zoom into that region, it's over MEG-P2, and what you will see is that nothing was revealed because the cutoff was 25 consecutive probes and 50 kilobases, and this, in fact, has 20 probes. If you change your threshold to 15 consecutive probes and 35 kilobases, then you will actually see that. The software will help you find that. So, very important about cutoffs and size thresholds. So, to illustrate how these things change, there was a recent study by Wang in prenatal diagnosis that kind of looked at these things, and they looked at their settings, and they basically looked at other labs and their settings, and they said, well, how would things change? So the first thing that's important is if your array does not include SNPs, then you cannot identify all the things that I mentioned, UPD, triploidy, etc. So in the Wang study, a decreased diagnostic yield of 5% was evident for array platforms that lacked the presence of SNPs. As I said, the larger the number of probes on the array, the greater the potential to identify CNVs across the genome. And the Wang study then compared, let's say, platforms that had 44,000 probes showed a 23% reduction in the number of CNVs detected compared with investigators who used an array platform of 2.67 million probes. So there you see with 2.6 million probes, they detected on average about 808 CNVs across the genome compared to about 622 when you use only a 44,000 probe array. So the lab thresholds and cutoffs are important, and over here the Wang group used a very liberal threshold, which is why they saw a lot of things, and when they compared it to the 44K array, there was 23% reduction. But if you actually take that 2.6 million array and use stringent thresholds, what you'll see is the number of CNVs detected actually drops, okay? So this is the same array on the right where you are using stringent thresholds and you actually get the same amount as the 44K array. In other words, CNV yield on the 44K array equals the CNV yield on a 2.67 million K array, depending on the thresholds and cutoffs that the lab uses. So why is this so? And this is looking at my own data of a prenatal case where I said, just show me everything. Maybe hard to see, but there's a lot of like green and blue lines that reflect gains and losses. And I'll focus in on the X chromosome. And here you can see where I said, show me everything. On the X chromosome, there are 34 imbalances. And across the other chromosomes, there are 7 from chromosomes 1 to 12 and 3.6 on average from 13 to 21. When I start to apply thresholds, let's say show me everything with consecutive 10 markers, what you'll notice is that number drops, not only on the X chromosome, but across all the chromosomes. And as I increase the number and my stringency, that number is going to keep on dropping until such time as I'm using 100 markers, and on the X chromosome, there are no imbalances that I see, but still 1 or 2 imbalances across the others. You can then apply not only consecutive probe thresholds, but you can also apply size, and there you can see everything drops to 0. And it's important to note that I even get 0 when there is a threshold of 25 markers. So in the Wang study, the reduction of the number of CNVs detected was 23%, the practical reduction. And this is the important part for pathogenic CNVs, was only 6.2%. And so if you look at that, the total number of CNVs detected was 23%, but relevance was really how many of those were pathogenic. And that's only a 6.2% reduction. And again, if you use less stringent thresholds, it's only about 1.6%. And Sandy, I know I'm approaching, I know I've still got at least 1 minute, okay. So the last question is, why would clinical labs choose to use lower density arrays or more stringent thresholds? Because increased CNV detection rate does not equal increased diagnostic yield, okay? Not all CNVs are pathogenic, and you get an increased number of variants of unknown significance, which may increase patient anxiety. And if you look at fetuses with ultrasound anomalies or normal karyotypes, at least over here, when they used a high resolution array with low thresholds, you can see compared to other studies the number of variants of unknown significance was significantly higher. And for normal anatomy, again, a significant difference. In fact, about 2.5 times higher in the one study and about 4 times higher than the NICHD study. So this gives a lot of effort when you have variants of unknown significance on our clinicians, on our genetic counselors. Many of them turn out to be inherited. The Wayne study, greater than 90% of them were inherited. And for years, when we see something that's inherited, the central dogma, if it's in a normal parent, then the outcome should be normative. And this is my last slide that I'll show. There's obviously exceptions when dealing with CNVs associated with reduced penetrance and variable expressivity. But I want to emphasize that there is little evidence to support the notion that reduced penetrance and variable expressivity is a major concern for the majority of VUSs encountered in the prenatal setting. So I am going to end there, and if they allow, I'll take any questions. Thanks very much.
Quick question, don't escape. We run over by 20 seconds, so I'll let you have a question.
Okay, so the question is, what I didn't actually say is, arrays are going to pick up any imbalances. So that means you're going to miss balanced rearrangements like inversions and translocations. And the argument is that we know for the majority of these, the outcome should be relatively benign unless in the rare event it actually transects through a critical region of our genome, either directly in a gene or a regulatory region or something controlling it. So if it's a balanced translocation, the other argument is, well, what about reproductive risk for the parents? You're not really giving them forewarning. And I agree with that. The counter argument is that, well, today's age, next pregnancy, you're going to be getting an array anyway, so if it's unbalanced, you will pick it up. It doesn't help for the emotional side when they have miscarriages to kind of explain that. So, yeah, thanks very much.
Our next speaker is Dr. Nita Bora. Nita is an MFM geneticist from University of North Carolina at Chapel Hill in the United States. Her research focuses on application of genome technology to the prenatal setting. She's going to talk us about an approach to integrating whole exome sequencing to fetal structural abnormalities in clinical practice. Thank you. Thank you, Laura. I would like to thank ISPD for inviting me to present this work today. And I would like to acknowledge my funding sources, and I have no conflicts of interest to disclose. So, there's been a lot of talk in the conference already about what we can offer in the setting of anomalies. And our field has really come a long way. So in the setting of anomalies, I know many of you start with qPCR, and in my setting, we start with a FISH, and we do microarray. If the microarray is normal, and there's a lot of talk about, what should we offer next? In the past, we were doing targeted gene panels, but as many of the presentations in this meeting have shown, there has increased utility in diagnostic yield in exome sequencing, and then now we will move after that to whole genome sequencing. So how do we integrate all of this information into clinical practice? And I'm going to talk a little bit about our study at UNC, and we are also studying how this affects families and studying how they are responding to the technologies that are being introduced. So I'm not going to talk too long about the background on exome sequencing because I see that Bryn has taken away some of my time, and and I'm just going to blame it on him. But as we know in the PAGE study, the highest yield was in the multi-system anomalies, and in the Columbia study as well, we see that the diagnostic yield is highest in the multiple anomaly cases. So, I think we have to start thinking about what results do we report. And going to the debate this morning, it was a very nice debate about talking about secondary findings in the parents and how to address that, because we are doing trio whole exome sequencing. We can also, give patients an option if there's a decision aid of some sort, because some parents might want to only know explanation of the fetal findings. Other families may want to know the secondary findings in themselves. And then, you can also report carrier couple findings where couples are carriers for the same autosomal recessive condition that is unrelated to the fetal phenotype but could have consequences in the next pregnancy. You could, as Igna stated in the morning, report on childhood onset conditions, and there's a lot of options there. So how do we obtain this informed consent, and what results do we report to the families? In our study, it is a research study, and we have, when the patient signs consent, they do consent for receipt of findings that explain the fetal phenotype, medically actionable secondary findings in the parents, and carrier couple results. So at this moment, we don't have an opt-in for these types of results. They will automatically get these results, but in our next study, which is a whole genome sequencing study, there is an opt-in. And in our study, the sequencing is done on a research basis, but we Sanger confirm all the variants in a CLIA certified lab, so the sample is split between the sequencing lab and the CLIA lab, and that is so that these results can be used clinically and they can be placed in the medical record. And the Sanger confirmation step takes extra time and increases the turnaround time, and I believe in many of the clinical labs this step may not be needed because it's a CLIA sequencing lab. So as you can see here in the scheme of exome sequencing, this is kind of the way we think about it. We started out looking at fetuses with anomalies that were highly suggestive of genetic disorder, and then we opened our enrollment to including isolated single anomalies and any major structural abnormality. And in our cohort, as in the other cohorts, there's this trio exome sequencing with no diagnosis by microarray, and we have a genetic counselor that does pre and post-test genetic counseling. The variant analysis takes the longest amount of time, as many of you know, and we evaluate the genes and we evaluate the variants, and if there's a pathogenic variant with an overlapping phenotype that explains the fetal finding, then those are pretty easy, but of course, our ability to phenotype a fetus is limited, so that is a big challenge prenatally. And we also look at our exome sequencing data and look at the sequencing data to see if there is evidence of copy number variant abnormalities that may be below the resolution of a microarray. And we have been able to identify some copy number variants in this way. And then we have a multidisciplinary committee which reviews all the variants, and then they're confirmed in the CLIA lab. This article was published in Prenatal Diagnosis, and I think there are special considerations for prenatal trio exome sequencing compared to postnatal, and really, in my mind, the biggest challenge is the lack of prenatal phenotyping. So if your patient is considering a trio exome, the more information you can obtain from the ultrasound, if you can get a fetal MRI or encourage your patients to have a fetal autopsy, if there is a demise, then those things really do help with the analysis. And this is our cohort, and as you can see, it's very highly selected for Caucasian and educated women. Highly selected because women that are highly educated self-select into the study. So they find out there's a study going on, and then they advocate for themselves, and they get in and they enroll. So I think one of the things I'm interested in is, are we inadvertently creating health disparities with all these new technologies, and how do we increase access? There's a lot of counseling points. So similar to microarray, if you were in the genetic counseling SIG breakfast, they talked about counseling points for microarray. There are a lot of special considerations and counseling points for exome sequencing, and this can take a lot of time. So that's another issue. We don't have a lot of genetic counselors, and how do we, adequately inform our patients about all these different issues? So these are some of the things that we talk about, and these are the way we explain it to the patient. And I know there's a lot on that slide, but I think that it illustrates my point that the counseling session will take a long time. And then we again do the post-sequencing counseling. Even if the results are negative, we have them come back. We talk to them about that there may be a genetic cause that we just couldn't find with the trio exome sequencing, and again, there's a lot that goes into the counseling for this. So for our study, our diagnostic yield is about 29%, and we've sequenced 94 trios, and we have had mostly fetuses with multiple anomalies. So we have the ability to Skype, counsel, and consent patients from across the United States. And so many of you in this room have, contacted us and sent samples to us. And so these fetuses have undergone a pre-selected or a genetics expert review. And of the fetuses with multiple anomalies, about 30% received a diagnosis. And then we also had fetuses with single anomalies, and 4 of those received a genetic diagnosis. And one of the 2 of those, I believe, were renal abnormalities. So the classification scheme is complicated, and I'll just point you to there can be a known pathogenic variant that, is de novo, overlaps with the phenotype, like something like OI type 2, and that's kind of a slam dunk. But then we have other, things like autosomal recessive conditions where there's a variant of uncertain significance in trans with a likely pathogenic variant that overlaps the phenotype, and those we call positive possibles. But as we all start doing more sequencing and we have the ability to deposit our data into shared databases, I really think that's going to help us understand the prenatal analysis a lot better. So these are results of the positive findings, and I think we're expanding our opportunity to understand the prenatal presentations of disease. So some of these conditions were never reported with a prenatal phenotype, and they're only reported postnatally. And so I think that is a very exciting aspect of this study. And we also have diagnosed some conditions where there was somatic mosaicism, and I think that, for instance, in the Costello syndrome fetus, that fetus had a very, very enlarged liver, which when I look back, that had been reported in mice, but not in a human fetus. So the classification scheme for uncertain results is this slide. Also has a lot of words on it, but it just illustrates again how complicated this can be with the VUS. And then I broke this down from inheritance pattern of the genes in our cohort, and we also had 27 fetuses that, or 27 families where there were multiple affected fetuses, and 8 of those got a diagnosis with the trio exome, and then the rest were single affected fetuses. And as you can see, about 12 of the 27 diagnoses were de novo. We do report carrier findings in the parents, and so we have had families where they had pathogenic variants that caused hearing loss. Another one where there was Sandhoff disease, and so these we report, and also medically actionable findings in the parents. So unfortunately, we've had cases where the fetus had severe arthrogryposis, and the family, desperately wanted an answer so they could find out information for the next pregnancy. We didn't find any answer to explain the fetal findings, but then we had a known pathogenic variant in a gene that increases the risk for ovarian cancer. So these are the types of things that come up, and in the end, that patient was very grateful to get this information, as there was a history of ovarian cancer in her family. So in my mind, and I'd love to hear from all of you, the issues that really need to be addressed are turnaround time, cost and cost effectiveness, healthcare utilization, healthcare access, electronic medical record, getting these results in the right place, whether there's a termination, the mother can use this for the next pregnancy, or the baby is in the NICU, and just really making sure that those results are in a place where the providers know how to look at them. And then, we reclassify the variants because as time goes on, the variants might get reclassified to pathogenic or benign. So we keep in contact with our families, but as this scales up, as you can imagine, it can be very challenging. And then use of BUSs for prenatal diagnosis and the highly tailored counseling that is required for that. So we do have a funded study to apply whole genome sequencing prenatally through the NICHD with Dr. Ron Wapner from Columbia and Dina Vanden Wever from Baylor. And so we are going to be looking at some of these issues. In terms of next steps for secondary findings, I think, in my mind, maybe something like a decision aid or a gaming app to help families understand the different types of results they can obtain. And then, I always think of myself as a clinician first, and so I'm very interested in how these technologies impact the family. And so we are also trying to, we are obtaining quantitative and qualitative data on all the families on how they respond to the information they receive from the exome sequencing, their genetics literacy, and also the psychological adaptation to the results. One thing we found is that, not surprisingly, women in higher socioeconomic groups do much better on the genetics literacy assessments, and there's also an increase. These women have a higher hopes and expectations that the exome sequencing will provide a result compared to what we counsel them about as the diagnostic field, which we say is around 25%. So these women have high hopes that they're going to get an answer when they enroll in the study. We also ask them what they hope to gain from the study, and a lot of the women enter the study for altruistic reasons. They don't feel that they're going to necessarily get answers, but they're just doing it for the future and to help other people. So from the parental side of things, in our study, we do have a high rate of Caucasian patients and college-educated patients. Like I said, women have high hopes and expectations about this test. And we also, so that is another question to address in terms of counseling. And we also found that women who get a result from the exome sequencing have higher test-related anxiety compared to women who don't get a result. They don't have increased anxiety and depressive symptoms, but they have higher anxiety related to the test. And so we have all these different validated behavioral and psychological adaptation to information scales that the behavioral scientists helped me with, and we submitted that to SMFM to present. And so we also are very interested in these ethical challenges, and so this was published in Prenatal Diagnosis, and I think that as we all do this, it's important to keep thinking about how we can integrate this into clinical practice in the best way possible for the families. And I think that there are many more studies that can be done in this area. There's a lot of questions to be answered still, in my opinion, and I would be happy to take any questions. Is there any questions?
Thank you very much. Just one question. What is your take on using whole exome and whole genome on patients undergoing invasive testing for maternal anxiety for basically no indication? Now, in 2012, ISPD, I think, was the first talk about exomes, and people said, why do we need this talk? Nobody's going to do it. So I think looking forward, some people are already doing it. So what is your take on that?
Yeah, this is a good question. Thank you. So, I think the studies are in women where the fetus has structural abnormalities. So I would say, there's not data, obviously, on women who are just anxious. However, I think certainly we all have women who come in and want a diagnostic test, and they ask for a microarray, and we do that, and we send that. I don't have a good answer. It's a really good question, and I'd be curious to hear anyone else's thoughts. I guess in terms of patient autonomy, if they're counseled and they know the Pandora's box they're opening up, and they are going to pay for this trio exome because they're anxious, it would probably make them more anxious, in my opinion, but I don't think we can stand in their way. Any other questions? Doug?
With the reclassification, do you have a set time? You look at it every 6 months of the year, or how often do you go back and look?
Yeah, so our study's a little different because we're also interested in looking at novel genes that could be critical to human development. So we're constantly reanalyzing the data over and over. So right now we're doing it every 6 months. Our cohort is not that big, but as it gets bigger and bigger, it is harder to do that. And so far, we've reclassified variants in 2 cases, and we were able to contact those families. But I definitely foresee, a time where we might reclassify something to pathogenic, and then we can't get back in touch with that family.
Thank you. Thank you, Lita. Okay, so in the interest of time, we'll move on swiftly now. I have great pleasure now welcoming Dean Nezetic up to the stand. Professor Nezetic has been is a local person, I would like to say, for the last 5 years is based here in Singapore, but being from the UK, I'm going to take you as one of our own, seeing as you've been there since 1987. So we're going to hear about the understanding the genetics of Down syndrome. No, thank you.
So I would first like to thank the organizers, ISPD, and Professor Mahesh Chalani for inviting me here. This talk may be slightly different to what you are hearing so far, and I have to first make a disclaimer. I'm not going to talk so much about the genetics of Down syndrome, because I think there are experts here who can teach me more about that, how it occurs, and the first meiotic desegregation, second meiotic division, non-disjunction, etc., etc. What I'm going to talk about is how understanding the genetics of Down syndrome can actually help us understand the genetics of very common and important diseases and biological phenomena. And this is something that a group of our scientists studying the genetics of Down syndrome have spent the last 15-20 years. So I don't need to introduce too much. Hello? Oh, sorry, I'm too far from the microphone. So the first report was published in the Royal London Hospital Medical Culture. I chopped something, I'll come back in the last slide too. But the real breakthrough was made by the group of scientists Martin Gauthier and Jérôme Lejeune, who published the first discovery that the actually trisomy 21 causes Down syndrome. So you know this better than me, but there are now, of course, there is a trend of diminishing the incidence of Down syndrome due to non-invasive diagnosis, something that this conference is best presenting the latest results on. But also there is the opposing trend of women having children later in life, therefore increasing the incidence of Down syndrome, and also people who don't want to be tested or Down syndrome. We're very grateful to the Down syndrome associations and communities, including the one in the UK and in Singapore, for their cooperation, and without which our studies would not be possible. And I think these studies are very important, not just to devise new strategies how to ameliorate the phenotypes of Down syndrome, both prenatally and postnatally. There are many efforts currently in the world, but also the communities of people with Down syndrome and their parents and associations are very proud in being able to contribute to, because they say if by studying us you understand more about very complicated diseases such as cancer and Alzheimer's, then we feel very proud and very inclusive and very supportive of these studies. So we'd like to increase genes, specific genes on consequence one is driving a number of phenotypes. So this is sort of how we look at the Down syndrome phenotype-genotype relationship. So some of the phenotypes are very frequent, will occur, will be very severe and occur in a large percentage of people with Down syndrome. Some will be very mild and some will not be present in many, or a fraction of people with Down syndrome at all. And so those range from reduced neuron numbers, suppression of solid tissue tumors, early Alzheimer's histopathology, early Alzheimer's clinical symptoms, the level of intellectual disability, and always very informed, and some behavioral changes that are listed here, and the heart defect, which is happening to about 4% of people with Down syndrome, and then a particular relationship between tumors and Down syndrome, increased childhood leukemias, but decreased solid tissue tumors. And the genetics is of course driven by these increases in the number, in the dose of chromosome 21 genes, but it's modulated by their allelic composition and possibly environment. So the studies, a lot of studies have been done in mouse, but it's very difficult to study Down syndrome in mouse because chromosome 21 is split in 3 different chromosomes in the mouse. So the last 10 to 15 years have done some very important studies, of which I'll mention just a few, by devising more ingenious and sophisticated ways of devising partial trisomies, partial monosomies, knocking out genes, so knocking individual genes, reducing them from trisomy to disomy while keeping the rest of the chromosome in trisomy. And some of these were also been studies by my collaborators Lisa Fisher and Viktor Tibulevich, who introduced a human chromosome into a mouse embryonic stem cell and then created a mouse that actually propagates a human chromosome. It's not an ideal model because it suffers from some deletions on the chromosome, but also nevertheless helps elucidate, understand the atrioventricular septal defect in Down syndrome. And then another model that I would mention is work by Roger Reeves at Johns Hopkins, who has used mouse modeling of Down syndrome with a segmental trisomy of the chromosome 21 to understand the phenomenon, or some aspects of the phenomenon of reduced solid tumor incidence in people with Down syndrome. So this mouse model that has the APC-min mutation that generates a lot of gastrointestinal tumors, you can see here, when it's crossed to a segmental trisomy 21, this is tremendously reduced. And what Roger Reeves then done is they crossed it to various heterozygous knockouts of the gene ETS2 and that actually identified this gene as the culprit in this segment, the short segment of trisomy 21, that actually ameliorates this phenotype. So why am I showing you this? Is to introduce something that Roger Reeves called tumor repressor genes. And the point of that is that this gene would not have been discovered otherwise had we not been studying people with Down syndrome and trisomy 21 as a phenomenon. So only by studying its increased dose we were able to see this repression, which then can have repercussions and further lead us to understand further biology of the tumors that could be used and exploited further in understanding cancers. And this would not be possible because this gene did not classically have haploinsufficiency or deletions or mutations in colorectal tumors, but when it's in an increased dose, it leads to these changes. So we also, in our lab, and I'll just speed up through this because it's all been published, we were utilizing these transchromosomic embryonic stem cells that had a human chromosome 21 on the back of the mouse embryonic stem cell, which allows us to then specifically target human 3' UTRs in messenger RNAs and silence them and actually reduce the dose of human gene only, therefore correcting the trisomy for one gene at a time in the chromosome, and try to dissect what that does to the phenotype. And this was all published, but one of the early phenotypes were mapped by these partial trisomic lines to 3 genes, and this was reduction in the master regulator of neural development, the neuroreceptor factor or REST, and this was mapped to 3 genes, and then when you count with the shRNAs for each individual gene, you see that in different combinations, only this one actually does the job and shows that this is responsible for this phenomenon. So us and others also found that this developmental difference in cell fate in trisomy 21 driven embryonic stem cells, where the cell fate of neuroectodermal is inhibited and cell fate of hematopoietic stem cells increased, is actually reflected in the epidemiology of tumors in Down syndrome, in the sense that in childhood leukemias, both myeloid and lymphoid, are all increased, whereas, for example, neuroblastomas are non-existent. And so, moving on from there, we started using induced pluripotent stem cells. So we generated a model where not only us, other labs generated similar models, but we generated a model from a person who was mosaic Down syndrome. So phenotype of Down syndrome, but half of the cells were normal. We reprogrammed them using a Yamanaka reprogramming and cloned individual trisomy and disomy cells. So we generated an isogenic system whereby we have multiple IPS lines that are trisomy or disomy. This was published and shown that the various phenotype increased amyloid material, accelerated neuronal aging, retarded neural progenitor cell growth, increased propensity for hematopoietic differentiation. This work is ongoing in terms of 3D cultures and trying to understand how this developmental issues form. But what is encouraging to see is that this decreased neuroprogenitor cell growth is actually introduced in the primary human neurospheres. So these came from Marcus Tsunami and Jerry Chan here in Singapore. And we're seeing concordance with our results in the IPS model. Towards the end of my talk, I would like to show you some of the results that are just coming from the lab and are not published yet, and are dealing with Alzheimer's disease in Down syndrome. And Alzheimer's disease, as you may know, is formed by some pathological hallmarks that accumulate with age, one of which is extracellular accumulations of this peptide called amyloid peptide that is carved out of a protein called amyloid precursor protein that is on chromosome 21, and therefore people with Down syndrome have an increased chance of getting Alzheimer earlier in life because of the 3 copies of the APP genes. And actually this has been proven because some people with Down syndrome who did not have the trisomy of this gene actually were spared of changes in the brain. So interestingly, there are people who only have this gene duplicated. It's called duplication of APP, 40 families around the world. And when you look at these people, they have the incidence of Alzheimer 100% penetrant. By the age of 60, all have dementia. Whereas when you look at people with Down syndrome, only about 60 to 70% of them by the same age will get dementia. So therefore, a group of us was teaming up to hypothesize that perhaps, besides the APP gene on chromosome 21, there are other genes that might be actually protected. So if you remember the previous example in Roger Reeves's work, we would never find these genes unless we study people with Down syndrome. So there could be Alzheimer's disease repressor genes. And I'd like to show you some of the latest studies that we've done using CRISPR to try to pinpoint one of those genes. So the work started in London. Before I came to Singapore, it was funded by the London Downs Consortium, London Down syndrome Consortium, which involved people from UCL, Alzheimer's geneticists such as John Hardy, Lizzie Fisher, and Victor Gulevich, mouse modeler. Sadly passed away, Annette Karmilov-Smith, who had a baby lab and was studying the infants with Down syndrome. We were trying to exploit individual differences in people with Down syndrome in their phenotype, in their cognitive and other abilities, behavioral problems, and then to dissect the people who got dementia from people who reached a certain age and didn't get dementia. So our role in the consortium was is illustrated here. So this kind lady with Down syndrome consented to give us a couple of completely non-invasively strands of hair, from which we grew primary keratinocytes, we programmed them to iPSs, and then grew neurons from them. And this is unpublished, so I'd appreciate it if you don't photograph it because it's currently under peer review. So we are able now to grow organoids, cerebral organoids, from these iPSs that are generated in this way. And interestingly, we can see amyloid pathology in these organoids in about 3 months. So we can see the amyloid positive. So this is a controlled human Alzheimer's brain. You can see the amyloid. This dye stains the flags. And you can see here examples of multiple people with Down syndrome with amyloid pathology in about 3 months. And interestingly, not all of them have it. So about 70%, roughly the same distribution as people with Down syndrome who get dementia by age 60, is about 70% have it. And interestingly, multiple experiments and multiple individual iPS lines, all concordant. So you either have it or you don't have it. So this, for example, this individual here has no pathology whatsoever, and we tested multiple organoids. So it would be interesting to try to explore this in the future and bring it to what you were calling diagnostic or preventative. What was the phrase you were using in your in the earlier talks in this session? So we are not there yet with this, but we hope to reach that point. So what is interesting is that we are trying to figure out why some people do have this pathology and some do and some don't. And it's not because they lost a chromosome. We tested the organoids for interface fission. You can see trisomics, disomics, they still hold on after 3 months, and their cortical part of the cerebral organoid still has 3 chromosomes 21. They also didn't lose neurons or have a skewing of astrocytes and neurons. They still have a sort of similar ratio of astrocytes and neurons. But what is interesting is that there are some genes on chromosome 21 that might be protected. So, for example, this is the APP gene, and the business part, this amyloid beta peptide that accumulates in the brain, is carved by these beta and gamma secretases. But there is another secretase which is encoded on chromosome 21 called BACE2, which the literature is divided in whether it functions as a causative gene that creates these toxic molecules such as the C99 and the A-beta peptides, similar as BACE1, which is the main beta secretase, or whether it's protective because it can cleave at position 19 and position 34 as a non-amyloidogenic cut. And we try to assess this using a brain organoid. So these are showing the trisomy and isogenic organoid, to show you they have multiple layers of human cortex in them. This is what it looks like, a 2 to 3 millimeter organoid floating in a dish. This is a bunch of organoids. Floating in the dish, so we grow a bunch of organoids and take a little bit of meat and see how much amyloid and what amyloid they're secreting. So this is the typical immunoprecipitation mass spectrometry done by Henrik Zetterberg's in Stockholm from our from our media. And these are several experiments which are showing that actually the BACE2-driven peptides such as 19 and 20 and 34 are increased in trisomy 21 repeatedly in repeated experiments compared to disomy. And interestingly, people with duplication of APP only who don't have BACE2 and 3 copy don't show this phenomenon. So this we tested this against another non-amyloidogenic catalyst, the alpha catalyst, doesn't show any differences. So when you actually look at the non-amyloidogenic protective cuts and you divide the BACE2 by alpha, you get these ratios that are hugely increased in trisomy 21 compared to isogenic, disomy, or duplication of APP only. And what is fascinating is that these ratios were produced in cerebrospinal fluid from people with Down syndrome. So actually, if you actually take cerebrospinal fluid samples, you will see the same ratios showing very highly significant differences. Now, to prove that these ratios are caused by BACE2, what we've done is a CRISPR elimination of one copy of BACE2. So here you see exon of BACE2. The yellow is a 7 base pair deletion introduced by CRISPR. That deletion fortuitously recreates the restriction site by joining this nucleotide to these 3 nucleotides and generates a second site for this 4-pepper enzyme. So you get this extra band. So we can quantitate the amount of band corresponding relative to the unchanged PCR product proving that it's only one copy of base 2 that was hit by this CRISPR. And this is reflected by the decrease in the protein amount in the Western, as you can see here, about 35% decrease. And this had the effect of decreasing the ratio that we measured before. But moreover, this organoid that was treated in this way started showing pathology. So this is, we call this one delta 7, it has a 7 base pair deletion. As you can see, this is its unedited organoid parental that didn't show any pathology. And when it was treated with a vehicle, showed no pathology. And this one shows pathology whether it's kept untreated or treated with a vehicle. But when you put complete beta and gamma secretase inhibitors in the dish, then you completely lose the pathology, proving that this really is amyloid. Not only that, it's actually driving the tau pathology. That this TT3 shows confirmation of the alpha tau, and you can see the quantitative data is showing that when you decrease third copy of base 2, you actually get the tau pathology which disappears by inhibiting the production of A beta. Okay, so I'm running out of time, and I'm not going to bore you with the further proofs that this really is the pathology in its quantifiable. Just to finish, I promised you a last slide of the role London Hospital Medical College, and John Langdon Down was the student here, and my lab actually started this work in this building, so I'm very proud that we're continuing the work started by John Langdon Down, and then moved it here, and these are the key people who did the work, and we recently moved into the magnificent setting at Novena, next to the Townsend Hospital, which is, and our work is generously funded by the National Medical Research Council of Singapore, Ministry of Education in Singapore, but also by local trust in the UK, and this is the group at the moment.
Thank you very much. I think that's a brilliant example of how you have to look at genetics, doesn't it? Describe, and there's not the solution to everything. You have to look at the whole biology, don't you? Does anyone have one quick question?
I actually have a comment and then a question, or question and then a comment. Did I hear you say that because of non-invasive prenatal testing for Down syndrome, the incidence of Down syndrome in live-born babies has gone down? Did you say that?
No, I would never state anything like that. It's
Okay.
not my field. All
Okay.
I'm saying is there are two trends. There's obviously a trend
Okay.
that this is becoming easier, and there's also the opposing trend that more babies are born later in life and so on and so forth.
Agreed.
So I'm not commenting on that.
Yeah, I think it's just a great opportunity to emphasize that there's no evidence that the rate of live-born babies with Down syndrome has gone down as a result of having cell-free DNA testing available. There's chatter in the Down syndrome community about that, but we've actually published data in prenatal diagnosis, and so that's not true.
I think it's actually very good news.
Yeah.
And very important for you to emphasize.
Yeah, so that's one thing. And then the second thing is, in my regular job as director of the National Institute of Child Health and Human Development, I want everybody to know that the National Institutes of Health has a major project called Include, investigating co-occurring conditions across the lifespan to understand Down syndrome. So, for example, people with Down syndrome have Alzheimer's disease at a higher frequency. The NIH is giving millions of dollars to do research in Down syndrome that will equally inform people who don't have Down syndrome. So we're looking at this across the lifespan. So you can Google NIH Include and see updates about the funding opportunities.
Thank you.
Thank you very much. Now we move to the selected abstracts for oral presentations. Our first abstract is presented by Sandra Dean from Edinburgh. Sandy is a rector of Gen QA in the UK, and she's going to talk about NIPT for microdeletions. Is it present or absent? The need to develop improved laboratory standards.
Thank you very much. So I'm aware that I've only got 10 minutes, so I'll be strict on myself. So these are my disclosures. Very quick start of this presentation, just to give you an idea of what we're trying to do and what the pilot EQA that we provided was about. So very basically, the principles of EQA is to provide an external quality assessment of the standard of the service being provided. So in very basic terms, we test the testers. And we do that by sending the same samples to all our participating laboratories, so all the testing laboratories, so we can benchmark their performance against each other. So they have all the same starting material, are asked to perform the same test, and then we can look at different standards of service and the quality of the service being supplied. Before we do that, we have to make sure that the samples that we produce and we distribute to our participants are fit for purpose and also testing agnostic. So we're not prescriptive as to the type of testing or the methodology that should be performed. We want to make sure that however you are doing the testing, you are doing that accurately and appropriately. It also gives laboratories a continuing measure of their performance. So if there's any issues in the laboratory which might not actually be test-based, it may be quality management or actually some training issues, can be detected as quickly as possible. And this in ongoing records of participation and performance is very good when it comes to accreditation purposes, when we can ISO standards, as that you have there a full record of your performance of your service. And this type of data is used by a whole range of different key stakeholders, not just your clinical users, but perhaps laboratories that you subcontract out to, or you actually are a subcontracting laboratory, commissioning, different types of funding areas, and also R&D and clinical trials. So what we have been doing is for the last quite a few years now, we're offering NIPT for common aneuploidies and NIPT for fetal sexing external quality assessment. Now, due to participant demand and the request to set up new EQAs, we provided last year, 2018, an EQA for NIPT for the common microdeletions. Now, we did perform a laboratory survey, and there was many laboratories, about 50 laboratories, indicating that they were setting up this clinical service. So we went ahead and delivered a very small pilot EQA. A pilot EQA is really to define whether or not the EQA is fit for purpose and whether there is a demand there for the testing laboratories. So it's very difficult to find these very precious samples, especially to be able to distribute to multiple laboratories. So we very kindly were supported by the RAPID consortium and project based in the UK, and we sourced 2 multiple maternal plasma samples, 4 mils of plasma each, for our testing laboratories. Obviously we can't pool samples because these are real patient materials or maternal materials. Following about a 6-year stability study, we now can actually distribute these real plasma samples at ambient temperature with no adverse effects within the laboratory testing. So one of the challenges was, what do we actually ask laboratories to test when we don't really know what they're testing for routinely? So we decided, based on the lab survey results, to select the 5 most common microdeletions that we assume to be testing, and they're listed here. The request for the laboratories was test using your routine testing procedures and report the results according to your local policy. And each EQA sample was provided with a clinical case scenario. You can see here we have a global spread of participants, but very small number. We have 12 participants who actually participated, and I think this is based on the survey results of many laboratories planning to implement clinical testing compared to those who are actually performing clinical testing in 2018. With EQA data, we get a very good snapshot of what's currently happening on the ground, and here, I'm not quite sure if you can see this, but there's a range of different methodologies being performed, with Harmony and NGS on the left-hand side of the graph being the most predominant. However, NGS can mean anything. Also, we have direct analysis of cfDNA. Again, we don't know what type of methodology that is, and also genome-wide next-generation sequencing, massive parallel sequencing. Again, not very descriptive as to what they're actually using to test. So this is case number 1. The clinical scenario was that a first cousin of this lady had a 4-week-old child who had been diagnosed with Creutzfeldt-Jakob syndrome, and she was anxious about her own pregnancy and had requested NIPT for microdeletions. The sample provided had no evidence of a microdeletion syndrome for those tested for, and really pleasingly, we were glad to be able to report that there was no genotyping errors. but very, very variable content on the way the data and what had been performed was reported. And I think that's something that's just as important as whether or not you're getting the right result, to minimise any misinterpretation of that result. So the graph on the right-hand side, your maximum mean score that you can achieve is 2, and you can see genotyping is up there, and interpretation is really quite dropped considerably, especially as there was only 12 participating laboratories. And also the clerical accuracy, so this is whether or not the patient name, date of birth, any clinical referral information had been transcribed onto the report incorrectly. So again, puts in doubt the accuracy of your test result if you can't actually confirm that the same patient has been tested. We can look at the scope of the test performed, as in which microdeletions were tested for, and those here in blue columns are those 5 that we indicated on the test request form. However, we also had 3 different laboratories who included and extended their scope of test and had another 6 different types of microdeletions included in their assay. However, one of the really big surprises of this EQA assessment was the scope of test, not just the extra microdeletions added, but the fact that 2 laboratories did not test for 22q11. Now, we assumed that that would be the most commonly tested for, so that was quite a surprise to our external assessors that these were not included in these 2 laboratory remit of their assay. Case number 2 was a clinical scenario for a first trimester ultrasound with IUGR and also heart anomaly. And we were testing for NRPT microdeletions due to maternal anxiety. This sample did have evidence of chromosome 22q11 deletion, and we had a couple of samples that went out with the duplication as well due to the limited availability of the material. So we were looking for a high risk 22q11.2 deletion syndrome detected, or DeGeorge syndrome, and also to report the low risk for the other microdeletion syndromes tested. And this often was omitted from the report, so it's very important to report results on all the tests that have been performed. So our external assessors were looking for that the high risk result must be confirmed with invasive prenatal diagnosis. And we've seen through the years with our NIPT aneuploidy EQA scheme that this is now becoming more common practice. However, this was not the case in the microdeletions. So it's about transferring the learnings from the testing that you do in a slightly different clinical indication or context into that similar type of service. And we were also looking for a referral to genetic counselling to be recommended. We had 2 laboratories that failed to detect this deletion or duplication. One was a true critical genotyping error, which I think with some looking back at root cause analysis is probably a limitation of the methodology performed. And the second laboratory had been supplied with a duplication, and this was out with the scope of the test, so we don't class that as a critical genotyping error. We saw a third of the laboratories with providing a report with no clear clinical statement about the significance of this high risk test result. Now, this was a learning that we saw and an improvement in the reporting through the aneuploidy schemes, but not through something new like microdeletions. It's a screening test, and we felt it's very important to outline the limitations of the test being performed. And a lot of laboratories included this on the report, but it was with respect to aneuploidy testing or fetal sexing. There was very, very limited information on the reports for microdeletion testing specifically. 58% of our labs had no description of the limitations of the test, insufficient information regarding the test limitations, or failed to provide their own sensitivity and specificity of the lab's values. Many laboratories just provided a reference which doesn't actually tell you about the performance in your hands, in your laboratory. So in a summary, the reporting issues that we observed was very similar again to NIPT and aneuploidy testing reporting. To see a clear result, often you have to look right through the whole report to actually find what the take-home message is. Avoid vague, wordy sentences. Sometimes I don't know whether it's because it was EQA, but we had long essays trying to describe what the test result was. We're looking for a recommendation to clinical genetics if there is a mutation detected. and further testing should be stated if that is appropriate in that test result report. We also want a clear understanding of what method has been performed and the subsequent limitations of that test. And also, just to note, and I know many labs are bound by the limitations of their LIMS or their IT within their hospitals, but a very clear layout of your results. A lot of people use bold or text boxes to report the result, and this is very helpful when you're looking for that test result. So just thank to Rapid very much for their support for the EQA material, our sample validation laboratories, and also our scientific expert advisory group and our assessors. Thank you.
Thank you very much. Is there any quick question?
Thank you, that's very interesting. The other thing that I've noticed is missing from a lot of reports is a risk figure. It just says low risk. And then you don't get a number. Is that 1 in 1,000? Is that 1 in 10,000? 1 in 100,000? For all this precision, we actually don't get a number on most of our reports.
Yes, that's something we have observed, and we've talked about that quite a lot in some publications and the EQA summary reports for aneuploidy. What we struggle with is a risk figure can mean very different things in the way it's been calculated. We also see a huge variation on the way that the test results are reported, whether it's positive and negative, and that can be misinterpreted as well. We also have some laboratories after an NIPT for common aneuploidy test result giving a karyotype, which again is completely inappropriate. So it is something that's difficult. There's two camps. One camp saying that you should put a risk figure on there, definitely with probability stated, and there's another camp saying keep away from risk figures because it's subjective and it depends on the way what factors have been included to calculate that risk, and you're better saying high risk or low risk.
Everyone walks in with an a priori risk though based on maternal age, so surely you can walk out with a post-test risk.
So you have to think about things like fetal fraction, you have to look at your limit of detection and your sensitivity of your own test result in your lab. You have to look at gestational age, you have to look at whether it's BMI of the mother. So again, it's variable, and not all laboratories base the risk result on the same metrics to start with. So it's a difficult one. I haven't got an answer.
Thank you very much. We move to our second abstract.
Okay, thank you. So the next poster selected abstract is from Yuval Yaron, who's from the Tel Aviv, Israel, and is going to give us a snapshot and a summary of maternal serum genome-wide cell-free DNA testing to detect fetal chromosome abnormalities in early and recurrent pregnancy loss and guide further workup. Thank you.
Okay, thank you very much. Thank you for the committee for allowing us to present. And also, I'd like to thank Tony Burrell and his team in Barcelona for wonderful collaboration. And here are my disclosures. Chromosomal anomalies are a common cause for pregnancy loss. So 50 to 70% of early pregnancy losses are due to chromosomal anomalies, such as cats and rats described here, but also monosomies and other abnormalities. But it's important to note that even in recurrent pregnancy loss, now defined as 2 or more pregnancy losses, the random chromosomal anomalies are the most prevalent cause, accounting for 37 to 30 to 57% of the cases, depending. And the risk for those increase with maternal age. And only about 4% are caused by unbalanced chromosomal abnormalities, such as unbalanced translocation inherited from a carrier parent. Recurrent pregnancy loss, as I had mentioned, requires quite elaborate workup that includes immunological studies such as lupus anticoagulants, endocrine studies, uterine cavity assessment, and commonly parental karyotyping. But this type of workup is quite extensive, it's time-consuming, it's costly, but more importantly, it detects a probable cause in less than 50% of the cases, and this is hardly surprising because, as I said, about 50% of the cases are caused by random chromosomal anomalies. So it has been suggested that testing the product of conception can allow you to guide further workup. However, this is not routinely advocated by many societies, but if you do it, it will detect a probable cause in about 50% of the cases. And this has importance. It has importance for psychological support, it has importance for counseling, but it has also been shown to be probably cost effective, because if you find a random chromosomal event, there's no point in checking the parental karyotype or doing other sort of things. And this has been described recently by Florencia Petracchi from our society, but also from Popescu and Human Reproduction. So while karyotyping the product of conception is important, it does have its drawbacks. It requires culture, but culture sometimes fails. The product of conception may be contaminated with pathogens. There is the risk of maternal cell contamination. So it has been calculated that the practical success rate of karyotyping product of conception is only 53%. Of course, if you use chromosomal microarray, you may get higher rates, but this is, again, is not a common practice. But recently, we've shown a decline in the use of DNC to remove the product of conception, and more patients now undergo medical management of miscarriage using misoprostol, so there's a lack of availability of tissue. So the objective of our study was to assess whether genome-wide cell-free DNA testing can detect fetal aneuploidy in early and recurrent pregnancy loss. In practice, the method used, a blood sample was taken from the patient for a genome-wide cell-free DNA testing using Verify Plus. This was funded for by Illumina. And this was followed by a transcervical CVS using fine forceps. And this is the success rate of the cytogenetic approach. So STC short-term culture in 82%, long-term culture only in 76%, combined in 89%, and in combining all approaches used, including qPCR, we were able to detect the karyotype in 95% of the cases, about a 5% failure rate. Now, mind you, this is not common practice because most places do not take the effort to obtain the sample in such a way and perform so many tests to obtain the karyotype. So we started off with a group of 118 patients. 9 patients declined. Of the 109 patients who consented, 5 patients did not have any cytogenetic results, so there's no comparison to be made. There was 1 broken tube and 1 failed the pre-sequencing DNA quantification analysis. So the total group that we had was 102 patients, for which we had both cell-free DNA results and karyotype. And this is the group demographics. 47% of the patients were experiencing their first pregnancy loss. 26 had their second pregnancy loss. 15 had the third, and 12% had the fourth loss or more. The mean gestational age, according to last menstrual period, was 9.7 weeks. So more than 50% of the patients were below 10 weeks. And of course, the size of the pregnancy, according to ultrasound, was small. As I said, cytogenetic analysis included the long-term, short-term culture and qPCR. And the trick here was the fact that we had to modify the log likelihood ratios compared to the ones used for ongoing pregnancies. In ongoing pregnancies, the risk, even in high-risk group, the risk of having a chromosomal abnormality is low. Therefore, you should set your cutoffs relatively high so that you don't generate too many false positive results. However, in our group, as I will show you in a minute, the rate of chromosome abnormalities was very high, as to be expected. Therefore, you should use less stringent cutoffs to allow you to maintain a high detection rate. So this was performed using receiver operator characteristic curve, and these were determined for the various chromosomes. So here are our results. As would be expected,
the rate of aneuploidy detected in miscarriages increased with gestational age. Overall, we had a 67% chromosomal abnormalities, which is in concordance with previous results. But the rates increased from 36% in younger patients younger than 30 to 90% in patients 41 or older. Interestingly, the rate of aneuploidy was about the same for patients experiencing their first, second, and third miscarriage. And only from the fourth miscarriage and onwards, there was a decline in the rate of chromosomal abnormalities that were random, but still, that's a high proportion of patients experiencing just random abnormalities. And this is the actual detection rate. So in green, you would see those abnormalities that were detected for each of these chromosomes, and in red, the ones that were missed. As you can see, the highest number of abnormalities are those rats previously described. So for the single aneuploidies, our detection rate was 83%, which is quite nice. And what I wanted to add here is that the fetal fraction was about 5.4%, but it ranged from less than 1%, and even in some of those cases, we were able to detect the aneuploidy to as high as 28% in the case of triploidy. Trying to use a certain cutoff for fetal fraction so that below that we wouldn't do the test didn't succeed. So there was no actual cutoff for fetal fraction above which the detection rate would be increased. For the complex abnormalities, however, we had less success. So there were two cases, one with a plus 16 and plus 21 that was detected, and another one was plus 13 and 7 that was detected. But for some of the monosomies and certainly for the mosaics, were less successful. Regarding the euploid cases, the specificity was 88%, so there were 4 false positive cases. Of these, 2 were trisomy 4, and perhaps the log likelihood ratio cutoffs should be modified once we have additional data. So overall, the sensitivity was 69%. If we include all the abnormalities with a specificity of 88% and accuracy of 75%, there was an additional case of a combined triploidy and plus 16, wherein the trisomy 16 was detected, but not the triploidy. So I did not include that in this success rate, but it can go up a bit. So in conclusion, the accuracy of cell-free DNA testing in recurrent and early pregnancy loss is 75%, which is greater than the success rate of standard karyotyping. This eliminates maternal cell contamination, and this can be used to direct further workup and reduce unnecessary evaluation. It has been shown to be cost effective. The poster number 57 is down already, but you can check it out. It has been shown to be cost effective. And this now can be used in patients undergoing medical management of miscarriages. So this could certainly be taken as an alternative to karyotyping product of conception. And this is the last slide. Our suggested algorithm for using cell-free DNA guided workup of recurrent pregnancy loss. It's a modification of the algorithm suggested by Popescu et al. So if it's a first miscarriage, not necessary to test. If it's a second miscarriage, perform cell-free DNA testing. If you detect a random aneuploidy, no further action needs to be done, none of the fancy workup. If an unbalanced rearrangement is detected, then it's an idea to do parental karyotyping. And if it's a euploid pregnancy, then continue with the recommended recurrent pregnancy loss workup. And I'd like to invite you to the Cogent Congress in Paris, where some of these topics will be discussed. Thank you.
So interesting time because we're running very late now. Would you be happy to take questions perhaps at a later date tomorrow with coffee or something? Yeah, thank you. Thank you. Okay, so we are aware that we're running very late. We have one more speaker and then we have our partner, our industry symposium in here. So please stay for that.
So our last abstract is from Greece. Danai Mavreli is going to present next generation sequencing detects dysregulated microRNA in late onset pregnancy. Thank you.
Thank you very much. Good afternoon, everyone. I'll try to keep it as short as possible. Preeclampsia affects 2 to 8% of all pregnancies worldwide. It is a major obstetric issue as it accounts for 10 to 15% of maternal deaths. Additionally, mothers who suffer from preeclampsia and their neonates are at increased risk for developing cardiovascular and metabolic diseases later in life. Preeclampsia is classified either as early onset, when symptoms develop before the 34th week of pregnancy, or late onset, when symptoms develop after the 34th week of pregnancy. Currently, the only treatment remains induced preterm delivery. However, recent studies show that early identification of women at high risk is highly beneficial, as administration of aspirin before the 16th week of pregnancy can prevent or minimize adverse pregnancy outcomes. Several biomarkers have been tested for their ability to predict women at risk for preeclampsia in the first trimester of pregnancy. So far, the best performance has been achieved by an algorithm combining mean arterial pressure, uterine artery Doppler, and serum levels of PAPA and PLGF. At a 10% false positive rate, this algorithm detects 100% of early onset preeclampsia cases and 80% of late onset preeclampsia. So the aim of our study was to identify differences in circulating plasma microRNA expression levels between women who developed late onset preeclampsia as compared to those with uncomplicated pregnancies. We focused on late onset preeclampsia because it accounts for 85% of preeclampsia cases. Circulating microRNAs represent ideal biomarkers as they are detectable in body fluids, therefore they can be collected non-invasively. They are easy to quantify and they're very stable. Briefly, we collected 34 samples from our biobank in the University of Athens. 17 were late onset preeclampsia cases and 17 controls. This was a retrospective case control study. Briefly, we extracted microRNAs using a commercially available kit. For the first phase of the study, we used 5 late onset preeclampsia samples and 5 controls, and used next generation platform to identify microRNAs. For the second phase of the study, we verified the results obtained in the first phase of the study using qRT-PCR, and then analyzed those data using bioinformatic tools. So in total, we identified 1,682 microRNAs, and out of those, 387 were upregulated in the late onset preeclampsia group as compared to the controls, 95 were downregulated, and 1,200 showed similar levels of expression. Statistical analysis, as you can see in the volcano plot, revealed microRNA 23B and microRNA 99B significantly downregulated in the late onset preeclampsia group. Results obtained using next generation sequencing platforms were verified using qRT-PCR. Further analysis revealed that both microRNAs had similar area under the curve. Further analysis, pathway analysis, showed that putative target genes of the 2 microRNAs are involved in pathways known to be associated with the pathogenesis of preeclampsia, such as insulin resistance, Th17 cell differentiation, and the EGFR pathway. As far as we know, microRNA 23B has not been previously associated with the pathogenesis of preeclampsia. However, it is known to have a role in cell cycle control, proliferation, cell differentiation, neovascularization, and in vitro studies showed it is also involved in angiogenesis. And even another studies as well has shown that it is involved in T helper 17 cell differentiation. An imbalance in that process is known to be associated with the pathogenesis of preeclampsia. On the other hand, microRNA 99B was one of the non-coding RNAs involved in the pathogenesis of preeclampsia from a study by Yoffe and colleagues. Its target genes are also involved in cell cycle control, proliferation, and differentiation. Mouse studies recently have shown that it is also involved in cardioprotection, so this is interesting, and I'm going to talk about it a little bit. They used uninephrectomized mice. They administered DOCA and sodium chloride, which induced hypertension, which resulted in cardiovascular and renal injury. They also observed that microRNA 99B levels were reduced in those mice. Following, they administered those mice with metformin and observed that cardiac and renal function was restored, as well as levels of microRNA 99B. So this suggests that metformin could be acting through microRNA 99B, and therefore metformin should be further investigated as a potential preventive therapy for preeclampsia. So in conclusion, this is a pilot study that shows that microRNAs could potentially be used as diagnostic and therapeutic biomarkers for late-onset preeclampsia. However, follow-up experiments are needed to further validate those findings. Thank you very much for your attention.
Thank you very much. Well, there's no time for questions. We can continue at the Collaboration Center if you want. Thank you everybody for attending this very interesting genetic session. But stay where you are because we continue with the Perkin-Elmer Symposium.
I want to go.